Greetings and welcome. We're talking today about measures of central tendency. What I mean by central tendency is there a way if I have a list of numbers, all right, actually let's just get a list going here. Let's say I've got, I don't know, some numbers like 12 and 17. I'll actually list these in order too, just to be nice. 18, and let's say I've got, I don't know, 21, 32, and let's do two more, 33 and 41. Bam, there we go. So here's a list of data, and I want to measure, I want to have a number that quantifies what is, where's the center of this list, right? If I wanted to find a way to talk about what the centerness of this was, where does the center tend to be? That's what I'm referring to here. And we actually have a few different types of centers to speak of. And you've seen most of these before, I believe, but the first that we'll talk about is the mean. All right, and this one most typically is referred to as the average. If someone uses the word average, they're often referring to the mean of the list. However, the three measures of central tendency we'll be describing today are all technically averages. All right, they're types of averages. So you have to be careful that that word can be used generally to describe all of them, but kind of culturally, if someone says, what's the average of these numbers, they're referring to the mean. And does anyone know what the mean is, or do you have a way of describing the mean? Sure. Add all the numbers and divide by how many there are. Divide by the quantity. Okay. So, now writing a formula for that actually would be kind of weird, I'd imagine, right? So the mean is sometimes referred to as x bar, and I guess if I had to find a way to describe this, you could say x1 plus x2 plus x3 plus ... all the way to plus x sub n, right? I'd add them all up, and then I would divide by the number of terms, and in this case, how many terms are there? It's like n many terms, right? So that's how you would calculate the mean, the x bar. Now, to write this in another format, x bar is also equal to 1/nth multiplied by, so 1/nth is really accomplishing this divide by n piece, right? Multiplying by 1 over n is the same as dividing by n, right? Do you guys agree? Multiplied by, and here, catch this, the sigma, what? And I just want to point out that that's not this symbol. It's not like a sideways M. The top and bottom lines are parallel to each other, okay? But that's the Greek letter sigma, which is the Greek letter S, all right? And the reason they use the Greek letter sigma here is S is used for sum, all right? So I'll just say over here that this symbol is sigma, all right? The letter S is what it's referring to, and mathematically speaking, it means sum. And actually, perfect example, I might be able to open up this window of Excel and notice, say I wanted to add up this list. Notice there's an auto sum button up here, and what symbol is that? What? That's a sigma, friends. Would you look at that? So if I hit sigma, bam, it just auto summed that. How great is that? Good stuff. So I just want to point that out, right? Sigma, there it is, culturally accepted. It is the symbol for addition. So, and when you use sigma, you actually have to tell it something. So you'll have a starting point, So I'll say, well, start from I equals 1 all the way to I equals n of the following list, x sub I. All right? Well, let me, so this I is referred to as the index of summation. X sub 1. So like, kind of like how this was x, then a little subscript 3. So that's a sub 1. So yeah, so this is referred to as the index of summation. It's kind of like your counting variable, I guess, is what I would describe it as. And basically it's just saying this part here means this right here. Those are mathematically equivalent. All right, it means, all right, plug in 1 for I get x sub 1. All right, and I'm going to add that. I know I'm adding it because I've got a sigma. When I plug in the next number, plug in 2 for 1. Okay, so x sub 2. So x sub 1 plus x sub 2. And then keep going. Plug in 3 for I at x sub 1 plus x sub 2 plus x sub 3. And how far do I go? How high do I plug in for I? All the way to n. Okay, so that's what that means. It literally just means adding the list of x sub 1 all the way to x sub n. So we'll actually get used to this sigma notation later on. I also explore it more in pre-calculus. And actually calculus uses that symbol as well. And if you're wondering, here is the capital letter pi. All right, lowercase letter pi has the little squiggle. But capital pi is their letter P. And if I replace this with a P, instead of adding all of them, it would multiply all of them. P is for product. All right. So instead of like writing a list of, adding all of these things, they use sigma. It's shorthand. It's like when the Greeks wanted to text each other and they use LOL instead of laugh out loud. It's really what it is. And I want to point out it's actually more powerful than just adding up a list of numbers. I could also, what if I wanted to add the list of all of the squares of these numbers, right? Or x sub 1 times 3 and add them all up, right? I can actually do a lot of different things with it. Not just add up a singular list, but I could have all sorts of other operations taking place within there. But anyways, I just want to point out that if I add them all up, which is what this index, not the index, but what the sigma here means, and then divide by n, that's the average. That's what you guys described, so it's just a mathy way of writing it. Right, so I just want to get us used to that sort of notation. So for our previous example, all right, our previous example, let's find the mean. So here's our example, right? So x bar is going to equal, well, let's add all of these up and multiply by n. Well, how many are there? There are 7 of them. So n is equal to 7 in this case, right? So I'll have 1/7 times their sum, and I'll grab a calculator for this. 12 plus 17 plus 18 plus 21 plus 32 plus 33 plus 41 is 463. So x bar is that divided by 7, which is 60. No, wait a minute. Is that can't be right. Why would it be 66.14? Guys, what did I do? Oh, I typed 322 at some point. I was like, that doesn't work. That doesn't work. Let's see. 12 plus 17 plus 18 plus 21 plus 32 plus 33. All right. Now I've got it spaced out. 174. That sounds better. Huh. Silly me. 24.857, roughly. All right, would be my x bar, or my mean, or my common use of the word average, right, is what I'm talking about. Right, so add them all up, divide by how many there are. Excellent, excellent. So here's a classic math problem. Let's say you're a student, all right, as a student, you have 3 test scores, which are the following. All right, let's say you've scored like a 78. Let's say you've scored maybe like an 82. And let's say you've scored like, I don't know, maybe like an 87. All right. And you want, you have 1 test remaining. And you want an 85 average. Or mean. What do you have to score on your remaining test? What score do you need? Right? So a common question that students might have, right? If you're shooting for some desired end outcome, this is what we're looking for. So, well, let's define a variable. Let's say x is equal to the last test score, right? And once I take that last test, how many test scores will I have? 4, right? And I know x bar actually in this case. What is x bar? My desired average is 85. So I'm going to set up an equation and solve it, where I'm going to say that x plus 78 plus 82 plus 87 divided by 4, right? Or I could have it set up this way, multiplied by 1/4, whichever way you want, is going to equal the average I want, 85. Right? And I want to solve for this final test score. What is that grade gotta be? Right? That I have at least that. Actually, I guess I could even, instead of just an equal to sign, I could make that a greater than or equal to sign, right? Maybe I'm cool with anything better than that. So to solve this, what do you think we would do? Well, yeah, you could, and I mean, I'm actually, in this case, going to get rid of the 1/4 by multiplying by it, just so I don't have to divide all of those numbers by 4. Let's see, so I'll have x plus is greater than or equal to 4 times 85, 340, and let's say I add 78 plus 82 plus 87, 197. All right, and now I'll subtract it from the other side. So same idea of what you would have done. The one common mistake that people would do if they did distribute this 1/4 is they would just forget to put that x over the 4. Is the only thing I'd be cautious of. Let's see, so x is going to be greater than or equal to 340 minus 197. What? Is it really that bad? Did I make a mistake again, guys? 78. Guys, why can I not plug numbers in a calculator today? This is so sad. 197 wasn't the sum. Sorry. 78, not 28, plus 82 plus 87. 'Tis a shame. It's 247. All right, that feels better. And when I solve, I'm going to get x is greater than or equal to 93. for my final test score. Now, another thing I think about when I think of averages is I kind of think of like a seesaw, I guess. This problem can actually be solved a little bit differently. 78, 82, 87. And then blank. Because I want my average to be 85, I kind of can do this like little over-under thing. How much under 85 is 78? Right, it's 7 under. 82 is under by 3. 87 is over by 2. And basically, I need this to be greater than, basically I need the over to balance out with the under. All right, think about it like on a seesaw, right, literally, right, if I had like a seesaw and I want to make sure it's balanced on both sides. That's kind of like a quick little mathy way that you can think of averages sometimes. So how much more over does this last number have to be? Well, 7 and 3 are 10 under, so 2 and 8 would be 10 under. And 85 plus 8 is, in fact, 93 for my final number. So I just want to point that out. That's kind of like a neat way to think of averages, is this little over-under sort of concept. And that might be helpful at times. I don't know. So there's the mean, the X bar. Another concept or average that we'll talk about for our list, measure of central tendency, is median. And we've already seen that today. And could you guys describe the median? Right? It's the middle. All right. So the median of a set of data is the middle value. All right. Actually, let me put it this way. If it's an odd quantity, it's the middle number. If it's an even quantity, it's going to be the average of the middle numbers, or the mean of the middles, because you'll end up having two numbers in the middle in that case. So I just want to point out for that possible case that could happen. So when looking at our list, right, since I have it in order, I guess that's important, right, is middle number when it's sequenced. What's my middle number going to be? Yeah, it looks like 21 is the middle number, which in this case it was kind of obvious. So I could kind of base that off of the fact that there was 7. 7 divided by 2 is 3.5. So 1, 2, 3, and then this number would be the middle one. 7 was odd, so I knew there was going to be a single middle number. You also can kind of do this trick, which I usually mess up at some point, is cross off 1, cross off 1, cross off 1, cross off 1. And then you end up finding your middle that way. But usually I forget which side I started on by the time I'm in the middle of a long list. And then that's not very helpful. So yeah, finding the middle number, the mean would be 21 in this case. So, or sorry, the median. So the median is 21. So notice for the same list, up here I had X bar was 24, right? And down here I have the median is 21. All right, so as far as which of those is the quote-unquote better measure of central tendency, they're both measuring the center of that list of data. They're just doing it different ways, right? So sometimes it's worth knowing, you know, multiple types of averages, I guess, and kind of understanding that maybe their strengths and weaknesses at being able to measure data, right? Let's say, I guess the median wouldn't be very good at measuring the center. What if this was 41,000, right? This is one number, I guess, because I had commas there, I suppose. If I have 41,000 as my last number, 21 is still my median, but maybe that doesn't give me like a sense of scale of, maybe how much this number was really pulling up the mean, right? So there's, things to recognize about understanding kind of like what that measure of central tendency is actually telling you. So yeah, median, it's not that bad. The last type of central tendency we'll talk about is the mode. And the mode is the most frequently occurring value. Or number. All right, so it's not the largest number, it's just the one that occurred most often. And in our case, there actually is no mode. And actually, no mode can occur a couple different ways. So there's no mode here because all of these were equally likely, right? They all occurred once. But let's say I had this list, 12, 17, 17, 21, 32, 33, and 41. In this case, the mode would have been 17, right? But it turns out if, let's say I had 12, 17, 17, 21, 32, 32, or, well, yeah, there we go, and then 41. In this case, it's actually a double tie, right? Where I had 17 and 32 occurring equally often. And when it's a tie between two, it's called bimodal. All right, bi like bicycle. There was two modes. Whereas if it's more than a two-way tie, it's just no mode, right? I mean, technically I could have been like, this one's septuple modal, but like that's not actually helpful anymore, right? Mode is the most frequently occurring number. So mode is a type of average, okay? I don't think it's that valuable as the other ones necessarily. And obviously, in my mind, the number that most people think of when they think of averages or measures of central tendency is the mean. And that seems to work out pretty good. So let's look at some different arrangements of data. One thing I want to talk about is a stem and leaf plot. Stem and leaf plot. Here we are. And a stem and leaf plot looks kind of like this. It's just a different way of arranging a list. And it's similar to a frequency distribution in some ways. Just the way it's arranged is different. So a stem and leaf plot, let's say of our starting list, here's the classic numbers coming back. For this, I would probably set up a stem and leaf like this. I think I'll just show you what it is. So I'm going to have a vertical line. On the left, I'm going to have some sort of digit, I guess. So in this case, I think I'd only need 1, 2, 3, and 4. Where this is the stem. All right, and on the right-hand side of that bar are going to be the leaves, right? Stem and leaf, right? And the stem, just because I see a 1 here doesn't necessarily mean that 1 and a 0 represents 10. This number doesn't necessarily have to represent the tens place, or this doesn't have to represent, right, 20s and 30s and 40s. This could represent the hundreds place, or hundredths place for that matter. In fact, what you end up having to have is some sort of a key to decode the stem and leaf plot. But for this particular one, my key is going to be this, where I'll have 1 line 2 equals 12. all right? But I could have had that equal 120, all right? So I just want to point that out. Or I could have had it equal 1.2 or 0.12. So whatever the key tells you is what they'll actually represent. So since I know that now this represents the tens, all my stems, tens places, now we'll fill out the leaves. And the leaves, I'm not going to write 12 here. I actually only write the remaining digits. So I'm going to write 2, I'm going to write 7, and 8. And for a stem and leaf plot, if I had multiple 2s, I would actually write both of them. All right. So you want the quantity of numbers is going to be the same in a stem and leaf plot as they are in the regular list. And you actually also are supposed to write them in sequence. So if I shouldn't, for instance, if I found another 2, I shouldn't write it there. I want to make sure this is in order, right? Increasing magnitude. So let's fill out the rest of this. So for the 20s, I'll have just a 1 there. For the 30s, I'll have a 2 and then a 3. And then for the 40s, I'll have a 1. So you can kind of see that this is like a bit of a blend between almost like a line plot, a frequency distribution, and a list, where if I wanted, I could say, well, I have a frequency of 3 occurring in my class from 10 to 20, right, is kind of what that's saying. And if I have a stem and leaf plot like this, you know, it's just kind of a different representation of your list, your data. But sometimes you might have a problem presented this way, and then it might say, what's the mode? You know, and well, in this case, I wouldn't say 1 is the mode, right? Because that's 21 and 41. And in this case, there's still no mode. But if I wanted to find the median, I actually could still do my 1 there, 1 there. Man, I already got lost. 1 there, 1 there. Let's see, 1 there, 1 there. And I'd end up with 21 being the median, right? Which is what we calculated earlier. So I just want to point out, like, it can work. But when you do that, notice that I started on the left up here, and if this list was longer, I'd start on the rights down here, right? As I meet in the middle, since I have it listed in order that way. So stem and leaf plots, sometimes they show up on standardized tests, so make sure you know it. They are useless without a key or a legend, right? Something telling you what magnitude your numbers represent. So I just want to point that out. Now, the last thing we're going to do, we're going to take a dabble in some Excel. But what if I wanted to calculate the mean of data in a frequency distribution? So the mean of data in a frequency distribution here. So the mean, how did you guys describe mean again? Right? Add them all up and divide by how many there are. Now in a frequency distribution, let's see, I think I might have, yeah, so here's one, here's like a frequency distribution. I've got my classes and I've got the frequencies. Now, to add them all up, now imagine I didn't know the actual data values. Let's say someone just gave you a frequency distribution, right? Actually, let me insert a column here. I liked, that was the opposite of inserting. Come on now, friend. Insert a column here. And I'm going to just call this the class. And I'll concatenate this and throw in a little dash and then this, just so I have kind of like a, oh, actually that dash needs quotes around it, I just realized. Got to have those quotes, damn quotes, there we go. So now I've just got my classes kind of represented that way. So here's what a frequency distribution would look like. So if someone gave me this data and I said, let's find the mean of that data, the problem is I know I've got 7 values between 0 and 10, but I don't know their actual value. I mean, what if all 7 of them were 0? Or maybe I've got like some that are 1, some that are 3.7, some that are 8s. Like, I don't know, right? So if I want to add them all up, the best I'm going to do is get an approximation. All right, but if I wanted to pretend, find a number that represented all of that class, I mean, what do you think would be a good assumption of those values? What would you want to use if you wanted to like figure out what's a number that represents that class? If I wanted to add up 7 numbers to find the average. What was that? I'll throw your guess out. Well, yeah, you'd use the middle of it, right? And what did we call the middle? We called it the class mark. Or, yeah, in this case, it'll actually be the I guess it's the mean or the median of 0 to 10, right? The upper and lower limits. So instead of throwing some guesses for what those 7 numbers would be, I'll just say, let's just pretend all of them are 5, right? I mean, that's the best I could do with the information that I have, because I wouldn't have known the original list. And if I do that, I would want to figure out, well, I want to add up 7 numbers, all of which are 5. What's a quick way I could do that? If I'm assuming they're all the same number, instead of just saying 5 plus 5 plus 5 plus 5, right, 5 times 7, right? So if I multiply the frequency by its class mark, I now get a decent idea of where maybe the sum of those numbers would be, right? And it's a guess, it's an approximation, because I don't know what those actually are going to be. So let's actually work on writing down a formula for this. So x bar, all right, let's see, actually I might have to write some preliminary information. If x1, x2, these are capital X's, by the way, all the way through xk, all right, are the class marks, all right, so k is not the number of values that I have in my list. It is the number of classes I have in my list. So notice here, in my case, k would have been, well, I'd probably only need to go here or something like that. K would be the number of classes, right? So I think that's 9. But it's not the same as the number of values. The number of values would actually be the sum of the frequencies. So I just want to point that out. So those are the class marks in a frequency distribution. I'll just call that a capital F, capital D, with k classes. And F1, F2, F3, dot, 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 all the way through Fk are the corresponding frequencies. Right? So in that case, in my case, F1 would have been the 7, right? X1 would have been the 5. Right? And we said a moment ago, to find the sum of that whole class, we could probably just multiply 7 times 5, right? So then, that's actually, then the mean, arithmetic mean, I guess we do call it that, arithmetic, x bar can be approximated. And that's key. It's not an exact value, because in a frequency distribution, I didn't know my exact numbers. As follows. So x bar is going to equal, well, for each class, I'm going to multiply it by, or for each class mark, xi, I'm going to multiply it by its frequency, right? So for our first class, that product would have been the 75, or sorry, 35. 7 times 5 is 35. But I want to do that for all of my classes, right, to find the sum of my list, or approximated sum of my list. So I would want to do 7 times 5, and then 5 times 15, and 5 times 25, and 3 times 35, and add those all together. So instead of writing that, I'm going to use my sigma notation, where I starts at 1, and it'll, multiply class 1 by class 1's frequency, multiply class 2 by class 2's frequency. And how high do I have to do this for? How many classes do I have? I have k classes, right? So I'm going to go from 1 to k. All right? And that's going to end up giving me an approximated sum for my whole, right, list. And now I divide that by how many there are. So in a frequency distribution, what's a quick way I could find out how many numbers there are? If this is the only information I had. Which numbers? Right, yeah, the sum of the frequencies would give me the total number of numbers in the list, right? I know there's 7 here, 5 there, 5 there, 3 there, 2 there. If I add that up, the sum of the frequencies is going to be the number of elements. So how do I represent the sum of the frequencies? Well, sounds like another sigma notation problem. Let's see, so I'll have fi, and I'll want to add from I equals 1 to k. So we're going to set this up in Excel. We'll program this together. Or I'll program it now. I'll help you guys code it later. But for the sake of our video friends, they'll see me program it. So I'm going to want to multiply my frequency by my class mark. So over here, in fact, good, I did delete it. Excellent. So this column I'll just call x times, oh, you know what? I might not have deleted it. Aha. I had some hidden white code there the whole time. Secret. Let's see, actually I want to select this whole column and make its font black. Did I do that? I did, good. Alright, so this is going to be x times f, I guess I'll call it. So in Excel, I'm going to hit equals, and what two cells am I multiplying? The class mark and the frequency. So E4 times G4, right? And I hit enter, and there's that 35 we talked about. And instead of programming this formula all of those times, 10 times, I'm just going to click and drag it down, and it's done that for me. Right? So 105 is my estimated sum of the 3 numbers in this class, where I just assumed all of those numbers were 35. All right, so that's what that 105 represents. So I've multiplied those, but now what do I want to do with that list? I want to add all of those products. So down here, I'm going to hit equals sum, and I'm going to add this whole list. And there's 600. Okay? So for this whole numerator is 600. What's the other thing I have to find out? The denominator is the sum of the frequencies. I already know my frequencies. So this is going to equal, it looks like I already had it programmed in there. But I'll change the font to black again. Equals sum, and it's going to be the sum of these. Alright, so I've got the sum of the products of the frequencies and the class marks, and I've got the sum of the frequencies, and now according to the formula, I'm going to divide them. So I think I actually have that calculated here, x bar. And it's the same value all the time. I just have it repeated for a later formula, where this formula is going to equal what two things divided? This divided by 24, right? And in fact, it's always going to refer to those cells, so I'm going to dollar that and dollar that. And the reason for that is that when I drag this down, it won't. Notice here, it's still referring to those same two cells rather than the one that was two below it. All right, so that's called an absolute reference in Excel, where the formula will always keep referring to that value. Whereas here, notice it shifted down which two it was multiplying, right? It shifted down which two it was multiplying. Whereas if I dollared this, or even just dollared 4, because it's staying in column G, watch, I would actually get an error where, oh, I accidentally have it multiplying still by the 7, but that's not what I want. So I just want to point out that's what that dollar sign, it's referred to as an absolute reference. It's always referring to the same two values. So 25 would be my approximated, right, x bar, my approximated mean for this frequency distribution. And in this case, I can scroll over and I actually can calculate the mean of this list. Now, if I have the actual list, how would I find the average or the mean? Add them all together. Actually, let's see if it messes up when I do that. No, it worked, I think. I don't think the list word is there messing it up. Good. It knew to just add numbers, not words. So I would add them all together and then divide by what? Okay, so Excel actually has a formula to do that. It's called count, and it's going to count only the numbers in those cells. So I'm going to add them all together, divide by how many there are, and I got 25.25 is the exact average of this list. And compared to what my approximation, that's not that bad. 25 compared to 25.25, right? That's not that bad. Now, it turns out you don't have to program this every time. Excel actually does have a way to calculate the mean, and it's actually referred to as average. I think you've seen me use it before. So if I just average that list, Excel's giving me the same thing as my formula. Now the mode, the most frequently occurring value, I think Excel has, that's good because I would not have wanted to program the logic for that. But I think Excel's mode breaks. Let's see. So here I've got two 4s, right? And that's the most frequently occurring number. Now let's say I also have two 3s. It's actually not telling me that I have two modes. And let's say I also have two 6s. It's actually, it breaks on multimodal problems. All right, and actually notice it's telling me the 4 is the mode, even though I have a tie with the 6s and the 3s. So it's not even giving me the largest of the modes. It's just giving me whichever one was first is actually what's happening. So if this was a 3 and I've got the 6s there, right, or if I threw my extra 4 down there, it's just doing whichever one it calculated first. So so mode in Excel doesn't fully work. I just want to point that out. And median, I think there actually is a median as well for the list, and I get 20.5 as the median, so the middle number. And actually, let's find that out for ourselves. Equals, I can quick sort this. Bam, right there. How many numbers are there? 26 minus 3 is 23. So half of that is, blanking out, 11.5. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and a half. Wait a minute. The median's, wait, how many numbers do I have? Wait, 23 numbers, right? So there should be a middle number. But this is giving me a decimal. Did I do that wrong? No. No, there's 24 numbers.
Yeah, because you added the 3 and it didn't take it away.
Huh. Well, it still should be recounting. Huh.
Oh.
Well, anyway, so there's 24, so it would be between the 12th and the 13th value. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And yeah, between 19 and 22, the average between those is 20.5. Okay, so that's working out. So anyways, so there's some Excel calculations for us. We still got our frequency distribution and stuff. I just wanted to point out we could actually calculate some of those things automatically, and that's all good. So thanks for watching, Internet friends. Have a great day. Bye-bye.